Well, a very good morning to all of you again. So, today in the last class what we did, I had introduced multiphase flow to all of you, isn't it? I had told you what is multiphase flow and how is it different from single phase flow conditions, what are the applications of multiphase flow, why do we need to study multiphase flow, why is the need being more felt in the present day scenario as compared to the need which was felt previously. There were applications in the past also and the applications are increasing. Then there is an increasing pressure to improve the efficiency of the equipments. Now we are governing, or rather we are operating over several particular scales. We have started to operate from the micro scale, nano scale level to macro levels and to much larger ranges as compared to that, and therefore the need to study multiphase flow, to understand multiphase flow, to increase the efficiency of the equipment, to bring about a proper design of the operating equipments, to know the safe operating limits, to diagnose faults, to correct faults, as a matter of fact even to alleviate some type of defects. For all these things we need to know, or rather we need to know the hydrodynamics as well as the other characteristics of multiphase flow as the situation may demand. Now, when we were going through the applications in the last class, I showed you that there are a vast number of applications. If you remember this, they have started from, say, the applications. If I will just go through it in very short, we will find that there are a large number of applications starting from power system, heat transfer, process equipment till biological systems, geometrological systems and so on. And we find that there are a large number of variations. Okay. Somewhere it is ocean wave transport, somewhere it is the respiratory system. So, these things they do not seem to be connected in any way. But if we have to give about a unified approach to the particular type of study, then in that case what we have to do? We have to present some unifying principles. The first thing is we have to identify, as I had discussed in the last class, how multiphase flow is different from single phase flow. Now, we found out that in single phase flow the situation was it is either laminar or turbulent. We have to find out whether it is laminar or turbulent, which is already a very well defined technique to find it out. Once we know it, there is no problem at all. In this particular case also we have to know the distribution of the two phases. Once we know the distribution, because in this particular slide if you find in the first particular example, we find that simply gas bubbles rising through a bottle of lemonade. We find that small spherical gas bubbles are rising. Next, the other example, these are just practical, this common life examples which I have shown. When you simply pour water from a bottle, we find that when you pour water from a bottle and through a narrow necked bottle rather, we find that as the water comes out, large elongated bubbles enter here. Definitely the geometry, the topology of these bubbles are different from these spherical bubbles which are encountered in this particular case. So, the same physics, the same governing forces cannot be governing the rise of spherical bubbles, or rather certain forces are more important in this cases, certain forces are more important in this particular case. At the other extreme, if you see, it is just raindrops which are falling, or in other words a very interesting example, when there is rainfall you must have observed on the windscreen of the car, small rivulet sort of patterns, they come out and they flow in a very zigzag sort of a fashion on the windscreen. It is known as a meandering motion. Lot of interest has come up with respect to this meandering motion, and this is also due to an interplay of a different type of forces. Forces are the same, but some forces are important under certain circumstances, something else is important for certain other cases. So, therefore, we find definitely the physics of elongated bubbles rising through narrow necked bottles will definitely be different from the physics governing the meandering flow of rivulets on the windscreen during a rainfall. So, therefore, before we go to do anything for multiphase flow, or rather to be more specific, two phase flow situations first we will be dealing with. After that we might touch upon some sort of three phase flow situations as well. First thing we need to know is the distribution of the two phases. The first thing is the distribution. What it does, it governs the entire physics of the flow, and more importantly we know that since the two phases have a different density, as I have already told you. So, therefore, what happens, there is a slip between the phases, as I had explained in the previous class as well. So, the lighter phase tends to slip past the heavier phase, and this particular slip velocity, as I have already discussed in the last class, this particular slip velocity, it depends also upon the distribution of the two phases, and of course, it varies with a large number of parameters as we had discussed in the last class. Okay. So, therefore, since it governs the slip, it governs the heat, mass, reaction kinetics, it governs everything of two phase flow. The first thing which we should study is the distribution of the two phases and how the distribution it varies with different phases. Say air, water, what are the different types of flow patterns which are available. Instead of air, if we use a oil, how the flow patterns change, how they change with flow rate, and definitely how they change with the conduit orientation, the conduit geometry and things like that. So, we will be proceeding systematically accordingly, and today we are going to start the estimation of flow patterns. Now, from whatever we have discussed, it might appear to you that well, there can be innumerable number of flow patterns and we have no control over them, we cannot predict them ad hoc, and therefore, the situation is extremely difficult. Well, there are certain fortunate situations due to which some sort of delineation of flow patterns are possible. The main factors will be, first thing is effect of surface tension. What this does? If there is a discontinuous phase, then it tends to keep, and the size of the discontinuous phase is small, then it tends to keep those small discontinuous phases as sphericals or spheres. Now, before I proceed, I would like to clarify one thing. What is a continuous phase and what is a discontinuous phase? Any idea, anybody of you? Well, a continuous phase is that phase whose different parts can be joined by a curve which does not cross the interface. Is it clear? So, continuous phase is that phase which can be joined by any particular curved line where the curved line does not cross the interface at any point. On the other hand, the discontinuous phase is one where if you want to join two parts of the discontinuous phase, then definitely that curved line or that particular line, it has to cross the interface. So, therefore, we find that the first thing, or rather the basic factors which govern your or rather which delineate the different flow patterns is number one, surface tension. What it does? It tends to make small liquid drops and small gas bubbles spherical. This is number one. And the other important thing is, particularly for gas liquid or vapor liquid flows, there will always be a tendency of the liquid phase to wet the pipe wall. This you must remember. This does not again hold when it is a liquid flow. There we get some other interesting situations which we will be discussing shortly. Okay. But for gas liquid and vapor liquid cases, surface tension plays two roles. First thing is, it keeps the channel wall wet with liquid during gas liquid flow, and the second thing, it tends to make small liquid drops and small gas bubbles spherical. Now, remember one thing, that the first point which I have mentioned, that there can be certain exceptions to it. For example, when the tube is heated and the wall temperature is much higher than the saturated temperature of the liquid. Under that condition, what happens? Vapors will be generated at the wall and they may try to stick to the wall till a particular distance. So, for heated tubes, this does not always hold. There can also be some hydrodynamic instabilities due to which there can be gas phase or vapor phase sticking to the wall. But unless such a situation arises under normal circumstances, it will always be the liquid phase which will be wetting the wall for gas liquid and vapor liquid flow situations. Well, the other very important thing is gravity. Okay. Gravity in a non-vertical channel, naturally what it tends to do? It naturally tends to pull the lighter phase on the top. So, therefore, we will always have some sort of a stratification where the lighter liquid or the lighter gas, whatever is the lighter phase, that will be on the top and the heavier phase will be on the bottom. So, therefore, due to these two factors, more or less some order can be brought about in the totally apparently chaotic study of flow patterns which we feel. So, what I would like to do is, first I would take up say air water flows, and we would like to see that with gradual increase of one particular flow rate keeping the other constant, what are the different flow patterns that we will be observing. Then gradually we will be going to different situations, maybe we will be changing the pipe orientation, the pipe diameter, the fluid type, maybe we will be introducing one other fluid inside the pipe, maybe we will be heating the pipe, something we will be doing, and we will be seeing that what are the corresponding changes which come about in this particular case. Okay. So, now let us see for a vertical case, because the gravity will not be occurring under that conditions. For a vertical tube, suppose we take, we introduce say any gas liquid, we take for the time being air and water is being introduced here. Okay. Now, we have very low air velocity and it is about low to moderate water velocity. What do we expect? We expect that water flows as a continuous phase. Okay. Water flows as a continuous phase and discrete air bubbles are more or less dispersed in this continuous water medium. So, therefore, these bubbles, if they are very small, then they are definitely spherical. As they grow larger and larger, they tend to become deformed. Now, with time what we do? We gradually increase the air flow rate, keeping the water flow rate more or less constant. So, we are increasing the air flow rate. What do we find? Gradually the number as well as the size of these bubbles, they start increasing. Okay. So, gradually we find they become much more deformed, they deviate more from the spherical shape, and gradually some sort of a cap shaped bubbles, they come into being. Keep on increasing the air flow rate more and more. Okay. But in this particular case also we find that water is the continuous phase and gas is the discontinuous phase. More or less gas is more or less uniformly, or it is more or less dispersed within the continuous water phase. So, from here to here if we see, we find that maybe the shape of the bubbles have changed, but the basic characteristic remains the same. It is simply the water flowing as a continuous phase and the gas phase or the air phase, it is dispersed uniformly as discrete bubbles in the continuous water phase, where these discrete bubbles, they may be spherical, they may be non-spherical, they may be oblate, spheroidal, ellipsoidal, cap shaped and so on and so forth. Now, as we keep on increasing the air flow rate further, what we find? These particular gas bubbles, their size as well as their frequency both increase, and finally a situation comes when we find that they gradually coalesce and they formed such elongated sorts of a bubbles whose size is comparable to the tube diameter. Whenever we have this, we find that more or less now the flow pattern, it is characterized by such elongated bubbles which are translating uniformly through the liquid phase, and in between these bubbles we have the liquid mass, which are usually known as liquid slugs. Okay. Now, these bubbles, I have a schematic of these. So, these bubbles, if you see, these elongated large bullet shaped axisymmetric bubbles. Now, these bubbles are very interesting. Now, what we have observed is that these particular bubbles, they are characterized by a hemispherical nose. And a cylindrical tail. They have two portions and they are essentially axisymmetric and bullet shaped. Usually this has been observed, and under these circumstances what we find, the liquid from the liquid slug, it is sort of these. The liquid from the liquid slug, it actually flows downward as a liquid film. It is an annular film between the bubble surface and the tube wall. Okay. So, here we find a number of things. First thing is there are bullet shaped bubbles which translate periodically through the continuous liquid slug. Now, here we find that in this particular liquid slug there can be bubbles as shown in this particular figure, or they might not be aerated at all. The liquid slugs may be aerated, they may not be aerated. Now, the tendency of aeration that decreases with tube diameter, as I will show from some photographs shortly. Okay. And what happens is, from the preceding liquid slug, the liquid starts flowing downward as a continuous liquid film along the surface of the bubble, and it forms an annular continuous wetting film between the tube wall and the bubble surface. And then it comes down and finally it meets the liquid slug beneath. Now, when it meets, naturally in this particular conference a good amount of vorticity is produced. Due to this particular vorticity, some amount of air is sheared away from the surface of the bubble and they tend to aerate the liquid slug beneath. Now, usually the aeration is more to just below the bubble as compared to further downwards. Now, remember one thing, once these bubbles are formed, their shape does not change further with more introduction of air. What happens as we introduce more and more air? In this particular case, both the frequency as well as the size and the shape of the bubbles were changing in bubbly flow. In this particular case, once the bubbles have been formed, their shape does not change. If we introduce more air, the bubbles become longer and longer. But this hemispherical nose and a cylindrical tail, the axisymmetric bullet shaped shape, this remains unchanged. Okay? And if you observe, you find that in this particular case, the flow, it is characterized by a periodic flow phenomena. It is periodic. If you observe any particular cross section, what do you find? We find that in any particular cross section, I will just draw the slug flow once more, so that I can explain to you. And we find that the periodic this particular periodic phenomena, suppose you observe any particular cross section, you keep on noticing that particular cross section, what do you find? You find at one point there will be liquid flowing up, or there may be some sort of bubbly flow flowing up, then at some other interval of time in the same cross section you find that air is flowing up and liquid is flowing down as an annular film. Keep on observing, again you find that a bubbly flow mixture or pure liquid is flowing up, and after some time again you find that only pure air is flowing up and liquid is flowing down as a annular film. So, therefore, the main characteristic of this slug flow pattern is the periodic flow phenomena or the intermittent flow phenomena, and this is characterized by the alternate appearance of bullet shaped axisymmetric, this is very important, Taylor bubbles. These bubbles, they were first observed and they were studied in very details by Davis Taylor, and from henceforth they have been named as the Taylor bubbles. Bullet shaped axisymmetric Taylor bubbles followed by aerated or non-aerated liquid slugs. So, the thing is, if you compare the bubbly flow and the slug flow which has evolved from bubbly flow, just by increasing air, keeping everything else constant, we find that definitely the distribution is widely different here. Here it has a homogeneous appearance. If you observe one particular cross section, you will find the same thing. It is just a bubbly mixture flowing up, liquid is a continuous phase and the bubbles are distributed. There is no variation with time. If you keep on increasing the air flow rate, you come to a situation where you get a periodic flow phenomena characterized by alternate appearance of bullet shaped Taylor bubbles and liquid slugs. Now, again you keep on increasing the flow rate. What happens? These bubbles, they become larger and larger. As they become larger and larger, they become unstable, and then finally a situation arises when these bubbles, they get sheared, they get broken up, and they keep on oscillating up and down in the flow passage, and they present a totally chaotic and random flow distribution, which is termed as the churn flow pattern. Okay. So, what happens, that very nice periodic flow phenomena, that disappears altogether, and what we get a totally chaotic and random flow phenomena, where we find that there are chunks, irregular chunks of gases and irregular masses of liquids, they are flowing up and down in a totally chaotic and random manner, and it just presents, you cannot predict the distribution like that. It is simply a chaotic and a random distribution, and that is termed as the churn flow pattern. Keep on increasing the air flow rate more and more. What happens? These irregular chunks, what they do? They gradually start coalescing with one another. Okay. Now, the gas flow rate is very high, liquid is low to moderate. So, these chunks, they keep on coalescing, and then what it forms is, it forms a continuous gas core. Okay. And what it does, the wall has to be wetted by the liquid phase. Okay. So, therefore, it pushes the liquid towards the wall and it forms a continuous gas core, as you can see here, and it is separated from the tube wall by an annular film. Okay. So, therefore, from this chaotic and random churn flow pattern, we find that we entered into the annular flow pattern. In the annular flow pattern, we find that the gas forms a continuous gas core and the liquid is pushed towards the walls. It forms an annular film, just like the film which we had seen in the Taylor bubble region. Okay. And sometimes what happens, this film, it is usually wavy. When it is wavy, then part of this particular film, it is entrained by the gas phase and it flows as droplets or as irregular chunks or irregular wisps sort of a thing in the gas core. So, therefore, the annular flow, it can be characterized by a smooth interface or a undulating interface depending upon the relative velocity of the two phases, and we find that this main characterization is that there is a continuous liquid film on the wall and a continuous gas core between the two liquid films. There may or may not be droplets of liquid or wisps of liquid in the gas core. Some researchers, they have tried to differentiate between the wispy annular and the annular flow, but we are not going to do this for our particular purpose. We will be primarily be concentrated into dividing air water flow in vertical pipes in primarily 4 types of flow. One is bubbly, next slug, churn and annular flow. What is our intention is, we would like to keep the definition of flow pattern to a minimum, as well as taking care that each flow pattern can be governed by a definite set of characteristics and they have the same physics, so that the same laws of fluid mechanics governs them. So, therefore, broadly speaking, what we have done, we have first differentiated into bubbly flow, where liquid is continuous and bubbles are uniformly dispersed. So, it is a more or less uniform mixture of the two, where the gas phase is dispersed in the liquid phase. Next, we divide it into the slug flow pattern, where it is definitely it is characterized by the intermittent presence of gas and liquid, gas appearing as Taylor bubbles and liquid as liquid slugs, which may or may not be aerated. Interesting part of slug flow is very interesting in the sense that its hydrodynamics is comparatively more complicated and it occurs over a wide range of flow conditions, and more importantly, as you keep on decreasing the size of the tube, the range of existence of slug flow increases. So, therefore, as you proceed toward miniaturization, maybe you get slug flow over a much larger range as compared to normal size tubes. So, that is why slug flow is gaining more and more importance in the present day scenario of microfluidics and things like that. So, therefore, in this particular case we find there are number of interesting things. Firstly is the periodic flow phenomena. Secondly, if you observe slug flow, you will find that in slug flow there are regions where the liquid is flowing downwards and there are regions where the liquid is flowing upward. So, therefore, if you notice the wall shear stress, you will find that the wall shear stress, it keeps on changing direction with the passage of bubble and the liquid slug. In this particular region, the wall shear stress is towards the upward direction, and in this particular region it is in a downward direction, again here upward, again downward. So, therefore, with time we find that, or rather with position we find that the wall shear stress keeps on changing its direction. This is also one particular way of differentiating, distinguishing or identifying slug flow from the other flow patterns. Well, next after that we come to the churn flow pattern, which is the least understood, least studied flow pattern. I should say there is plenty of scope to study churn flow pattern for the time being. It is a totally random, chaotic, erratic mixture of two phase flow, not very well understood. And after that again we get the annular flow pattern, which is again a very well ordered structure with a gas core and a liquid film. Okay. So, these are usually the 4 types of flow patterns which we encountered in a vertical tube for unheated conditions. Now, simply keeping everything constant, instead of the vertical tube, we just make it horizontal. What are the changes that you would expect? Immediately you would find that gravity would start to act differently on the tube. Naturally, the lighter fluid, the air phase will be on the top and the water phase will be on the bottom. And so, therefore, immediately something which was not observed in the previous case will be observed here, that is stratification. So, therefore, if we go to the, if we just make the pipe horizontal, what we observe is an immediate tendency of stratification. At low flow rates of the two phases we find stratified flow, and then gradually as we increase the liquid flow rate or the gas flow rate, we find a waviness sets in and we come across a wavy stratified flow. As we keep on increasing the velocity, then we find out the water velocity, we find out that gradually these waves they become larger and larger. And then a time comes when the amplitude of the wave becomes so large that it can actually touch the upper wall. Okay? And again, if you keep on increasing the water flow rate, we find that it touches the upper wall, and then these particular gas phases, they start breaking up from one another, and then we have definite gas slugs separated by liquid slugs, but the gas slugs are usually concentrated or confined towards the upper portion of the tube. So, this gives rise to the slug flow pattern as we have observed for the vertical case, but here definitely slug flow pattern, it has got an asymmetric character. Okay. Bubbly flow which we had already observed there, annular flow which we had already observed there. Generally churning, it is not very prominent, but churning can also be observed under these conditions, but all this bubbly, annular, slug, they are all characterized by one thing here, that is the asymmetry in the flow distribution, because the bubbles, the Taylor bubbles, as well as if you observe the liquid film in this particular case also, you will find the liquid film will be thicker at the lower side, it will be thinner at the upper side. And with gradual increasing of the liquid flow rate, we find that gradually the effect of gravity decreases and more or less there is a uniform distribution. Okay. So, therefore, with moment we make the tube horizontal, by not doing anything else, we find that stratification sets in. So, we get 2 additional flow patterns, or in other words 1 additional flow pattern, that is the stratified flow. It is usually differentiated into 2 types, one is the smooth stratified flow, the other is the wavy stratified flow. Okay. Just because of the difference in the wave characteristics, some different treatment is necessary for the two, and therefore, we distinguish between the two. The other flow patterns are more or less same as we had observed in the vertical tubes, the only difference being that all the flow patterns have a tendency of asymmetry, which reduces with increasing phase flow rates. Okay. And the interesting thing we will come to see, it also reduces with decreasing the tube diameter as well. Under that condition also gravity does not play much role in this. Well, the next thing which I would like to deal with is, suppose we deal with a heated tube. Same vertical tube is standing, now we start heating it with a constant heat flux at the walls. Now, here what happens? Here certain additional factors start to come in. What are the additional factors? Number thing is, as this tube is heated, what happens? Gradually, say initially we have introduced liquid at below saturation temperature. So, the liquid, it starts getting heated. As the liquid starts getting heated, a point comes when vaporization starts to occur. When vaporization starts to occur, then gradually the vapor bubbles, they are formed at certain preferential sites, and they start getting detached and flow upward in the liquid phase, forming the bubbly flow pattern. Gradually the rate of vapor generation increases, and these vapor bubbles, they become larger, they start coalescing and they form Taylor bubble like structure, giving rise to the slug flow pattern. Again the heating continues. So, therefore, these bubbles, this Taylor bubble, Taylor like bubbles, these elongated bubbles, they become larger and larger till finally they coalesce and they become a continuous vapor core, and they form the, if you can see this picture, it will be much more evident. Initially we have single phase liquid, where liquid is below the saturation temperature, then gradually bubbles start forming and bubbles get detached from the wall, they flow up in the liquid, the bubbly flow pattern, then gradually we get the slug flow pattern, and finally we find that these slugs, they become larger and more numerous, they then form a continuous gas core with a liquid film and the annular flow pattern sets in. Now, after the annular flow pattern sets in, we find that now the vaporization, it starts to occur not more at the walls, but predominantly from the vapor liquid interface, and gradually the liquid film, it starts getting depleted. Remember one thing, in this particular case the liquid film gets depleted by two mechanisms. What are the two mechanisms? Firstly, some amount of the liquid, it gets vaporized into the vapor phase, and secondly there is a liquid vapor shear, therefore, some amount of the liquid, it gets entrained in the vapor phase. So, therefore, due to the coupled effect of entrainment and vaporization, the liquid film, it starts to get depleted. Okay? And then finally, a situation arises when there is no liquid film and there are only liquid droplets in the vapor phase. This gives rise to the droplet flow pattern. After the droplet flow pattern, of course, the entire liquid, when it has vaporized, we come to the single phase vapor region as shown here. Okay. So, in this particular case, in the case of a vertical heated tube, what you find, what are the basic differences as compared to flow in tubes which are not heated? What are the difference that you find? In unheated tubes and in heated tubes, what are the differences which we observe? Number one is the amount of gas and liquid, it keeps on changing along the length. Since the amount of vapor and liquid keeps on changing, the flow distribution also keeps on changing along the length. And as far as the flow distributions are concerned, what we find is that Here we find there is no churn flow, which is very prevalent in unheated tubes. The other thing is there is the presence of some droplet flow, which was not there in that particular case. As I had already told you that there is an inherent tendency of liquid to wet the pipe wall. So, therefore, this droplet flow pattern does not occur under normal circumstances in unheated tubes. So, these are the two basic differences between flow patterns in heated as well as unheated tubes. Okay. So, what are the additional factors in a heated tube? As we have already discussed, in a nutshell, if we have to mention, continuous change in phase fraction along the axial length. Okay. So, therefore, there is a continuous change, the vapor phase keeps on increasing, the liquid phase keeps on decreasing, just the reverse situation occurs if there is condensation. Next, there is departure from thermodynamic equilibrium. Okay. Next, there is a presence of a radial temperature profile. So, for this particular thing, what happens is, even if we find that the liquid mean temperature is much below the saturated temperature, but vapors start to occur because the wall is at a much higher temperature. The wall has exceeded the saturated vapor temperatures, therefore, vaporization starts, but if you find that the mean temperature at any particular cross section, that is below the saturated temperature. So, the next thing is presence of radial temperature profile and departure of local hydrodynamic equilibrium throughout. So, due to these four factors, we find that certain extra things come up in a heated tube when it is in a vertical position. Now, same heated tube, you think and tell me, same heated tube, I just make it horizontal. What do you expect under these conditions? In this particular situation, we find what happens is that gravity, well, this slide we will see it later. We find that gravity also starts to play a part in addition to the factors which we had already mentioned for vertical heated tubes. That means the presence of a asymmetric temperature profile, and then the other factors, continuous change in phase fraction along the axial length, departure from thermodynamic equilibrium, departure from local hydrodynamic equilibrium, presence of radial temperature profile. In addition to this, gravity also sets in, and therefore, it adds to the asymmetry of the flow situation. This flow situation, if you imagine, it will be something of this sort. Again, we start with liquid where T is less than T saturated. Okay. I will write it here, T less than T saturated. We start, so we have pure liquid till a particular portion, and then gradually the vapor bubbles, they start to come, they gradually detach from the wall, and then they start flowing, and then gradually they become more and more elongated, just like your slug flow sets in. And then we find a situation, due to asymmetry, there will always be a tendency of the vapor phase to be on the upper portion and the liquid phase to be on the lower portion. So, what we find is, we find that in the annular flow pattern, there is a continuous tendency of drying out and re-wetting. What happens? There is a continuous tendency of liquid, it gets dried out completely, but since there is a tendency of liquid to wet the wall, it again re-wets and again dry outs, again re-wets. So, such a situation arises. If we take up the cross sectional views of these cases, here the cross sectional view will be something of this sort. Then gradually we keep on observing the cross sectional views, it will be something of this sort, something of this sort. Then again, if we take a cross sectional view, the bubble will be larger and there will be smaller such bubbles. We take another cross sectional view, we will find a thicker liquid here and a thinner liquid here and things like that. Then we find that there will be portions when only the lower portion will be wetted and the upper portion will be dried out. In this particular portion, if we observe. So, therefore, this constant intermittent drying out and re-wetting this is something very unique. And finally, after that, of course, just like the vertical heated tube, here we have the quality equals to 1, here we have x equal to 0, here we have only vapor flow. Okay. So, therefore, we find that in a horizontal heated tube, since gravity also sets in addition to the situations which we had observed in this particular case of vertical tube, we find that there is a possibility of intermittent drying and rewetting of the upper surface of the tube in wavy flow or annular flow, as you call it. There is, and then gradually this intermittent drying period, it gradually becomes longer and longer. So, it is progressive drying out over long tube length of upper circumference of the tube wall in annular flow. Okay. And naturally, as you keep on increasing the liquid flow rate, then there is less obvious effect of gravity, and therefore, the flow patterns become more and more symmetrical and more close to vertical flows as the liquid flow rate increases. This particular situation was for a low to moderate liquid flow rates. As we go to higher and higher liquid flow rates, situation will be more similar to that which we have observed in vertical flows. Do you get it? So, in this particular way, we find that when we take a tube, what are the flow patterns? When same tube we just make it horizontal, what are the flow patterns? Same tube keeping it vertical, we heat it, what are the flow patterns? Same tube we make it horizontal and heat it, what are the flow patterns? So, these things we can understand from this particular situation. Now, let me take up once, this is another situation which can be encountered for condensation. Condensation also we find naturally initially the flow pattern will be annular and then gradually just the reverse of what you have seen. There we had started with bubbly, slug, annular. Here we start with annular, mist, annular, then some sort of stratification, then slug and things like that. And remember one thing, the range of existence of the different patterns, how long it will be bubbly, how long it will be slug, how long it will be annular, these things they depend upon the entry condition, the hydrodynamic condition and things like that. If a situation can be made such that the bubble rate of generation, bubble generation is very high at the walls, then probably we will not get a bubbly flow pattern at all during evaporation. We will directly or straight away go to the slug flow pattern. Such a situation can also arise. So, therefore, which are the flow patterns which are going to occur and what will be the range of occurrence of the different flow patterns, that depends upon the inlet conditions, the other hydrodynamic conditions and so on and so forth. Now, let us see if instead of air we simply introduce another liquid. So, instead of air water flow we have say kerosene water flow, okay, or toluene water flow. Kerosene water flow, it will be more akin to oil industries, toluene water will be more akin to mass transfer operations sort of a thing. Now, in this particular case what do we think, what should happen? Do not look at the figure for the time being, just try to understand the physics. What happens? There we had one particular situation. What was it? That the liquid will always wet the pipe wall. Here both are liquids, both can wet the pipe wall, isn't it? So, therefore, as we had only bubbly flow here, here we can have oil in water dispersed flow as well as water in oil dispersed flow depending upon the flow conditions. High oil, low water velocities, we have water in oil dispersed flows, low oil, high water, we have oil in water dispersed flows. Now, this is a very interesting situation. Dispersed flows we need in a variety of cases, okay. And if we are dealing with liquid cases, be it a reactor or absorber or whatever it is, we find that when we have oil in water flows, okay, we start with the low water, high oil flow rate. Then keeping the total mixture velocity constant, we keep on increasing the water velocity, decreasing the oil velocity, so that the total mixture flow rate is constant. We can do it. Say for example, we start with say U oil of say 1 meters per second, say just for, or maybe it is 0.1 meters per second and U water is say 0.5 meters per second. So, that the mixture velocity is 0.6 meters per second. Then we take another flow rate where this is 0.2, this is 0.4, this is 0.3, this is 0.3. In this way we keep on going, this is say 0.5, this is 0.1, and then finally we reach to this particular flow pattern. So, under these circumstances what we have a oil in water dispersed flow, and gradually as we keep on changing the flow proportions of the two, keeping the mixture velocity constant, we finally reach a condition where we have water in oil dispersed flow. And from very frequently we call one of them dispersed, the other inverted dispersed. Some researchers they prefer to call it oil in water, water in oil. So, different sort of nomenclatures are there in use, and we find that the transition from oil in water dispersed flow to water in oil dispersed flow, this is very, very important. Okay. It is very important because the total hydrodynamics changes, okay. The total interfacial surface area changes if water is dispersed in oil, if oil is dispersed in water. Suppose we have an organic phase and an aqueous phase. Okay. Say this particular, any particular reaction or mass transfer, it is controlled by the organic phase part. Okay. It is much more, and say suppose it is toluene, acetic acid is dissolved in toluene and we have a water phase. Acetic acid is more soluble in the water phase. What happens? It readily shifts from the toluene phase to the water phase. So, in this particular case we will have a better transfer, a better mass transfer if the toluene is dispersed as droplets in a continuous water phase. So, therefore, we would like to ensure toluene in water dispersed phase, and we would always like to see under what condition it will tend to become water in toluene dispersed phase, under which conditions we do not expect a very drastic increase in mass transfer. So, therefore, there are several such situations where we would like to ensure one type of dispersion, or we would very much like to predict the transition from one dispersion to the other. Now, remember one thing, when we are having this transition, what happens? What is happening initially? Suppose we are having say kerosene or toluene dispersed in water. Gradually as we keep on increasing one flow rate, decreasing the other flow rate, what happens? Gradually we find that the toluene droplets they start becoming larger and larger, water phase it starts breaking down to smaller and smaller droplets. So, therefore, there is a continuous creation and recreation of surfaces. Large amount of interfacial surfaces are being created and recreated, and lot of chaos forms under this condition. As a result of this particular transition, which is known as the phase inversion. For liquid cases, this particular word is very, very important. You are supposed to remember this. The phenomena of phase inversion, during which one particular dispersion inverts to form another type of dispersion. Okay. This is very important, and this is usually characterized by the sudden increase in the pressure drop. So, suppose you take a pressure drop reading, you find the pressure drop gradually increases, and moment you approach the phase inversion, there is a drastic reduction in the pressure drop, and again when you enter another dispersion, the pressure drop decreases gradually. So, therefore, if you plot say delta P or delta P by L versus say U mixture, you find that the pressure drop gradually increases, then when it comes to phase inversion, there is a steep increase, and again there is a gradual increase. This particular portion, this marks the phase inversion point. So, therefore, it is very important to know, because under this, just like flooding point, it is very important to identify this condition, because it is marked by a very high increase in the pressure drop, and therefore, under this particular circumstances, maybe what we have observed in our laboratory studies, several transfer operations are highly enhanced under this condition. So, this is something very special for liquid flows, you do not have it for vapor liquid or gas liquid cases. There is one other very important phenomena for liquid flows which we shall be discussing in the next class. Today I will just show you some particular pictures where you can see in this case it was a kerosene water flow in a vertical pipe. You can very clearly see kerosene droplets in the water phase. If you observe this particular photograph very carefully, you will find that the entire cross section is blue, it is marked by a kerosene phase, and some circular water droplets, large water droplets are there. So, here we have brought out the phase inversion very well. Here it is kerosene dispersed in water, here it is water dispersed in kerosene. Such a situation which will not get for air water or vapor water cases. Here also we have tried to do it at a higher water velocity. Here we find that the kerosene droplets are smaller, and in this case water is very finely dispersed in kerosene. It is sort of an emulsified flow. So, this is something very special for liquid cases. Okay. So, there are certain other interesting factors for liquid cases which we will be taking up tomorrow, and then we will go to some other interesting or unique features of flow patterns for different geometries, different flow conditions, and so on and so forth. So, tomorrow we will be continuing this lecture and we will be studying more about flow patterns tomorrow. Thank you very much.